Hey everyone, and welcome to this explainer. I'm so glad you're here today. Look, if you're the kind of person who really loves peeling back the layers to see how things actually work under the hood, you are in the exact right place. We're jumping right in. Today, we're unpacking the invisible mechanics that keep basically every piece of software you use organized. We're diving into a fundamental computer science concept called the stack. And, more specifically, we're going to look at why putting strict limits on what a system can do is, surprisingly, its absolute greatest superpower. So, to get us started, I want you to think about a scenario we have literally all been in. You know, you're typing up a long document, or maybe you're writing some code, and you make a mistake. So, you hit undo, and maybe you hit it 5 or 6 times in a row. Have you ever wondered how your computer magically remembers the exact sequence of your past actions so it can perfectly reverse them? And in the exact reverse order you made them? It doesn't just toss all your keystrokes into some random digital bucket. It actually uses a very specific, highly organized structure to track your every move. And the secret behind that magic is a data structure we call a stack. It's a linear data structure that operates on a super strict rule called LIFO. That stands for last in, first out. Now, this is different from a normal list or an array. With those, you can just jump in and grab data from anywhere, the middle, the beginning, wherever. But a stack forces you to follow one rule. You can only insert or delete items at one single end, which we call the top. So the very last thing you put in is always the first thing you take out. I like to think of a stack as a highly disciplined pile. And I know what you're thinking. When we talk about restricting access to just one end of our data, it kind of sounds like a limitation, right? Like, why would we want to limit ourselves? But here's the crucial thing. That restriction is incredibly deliberate. By forcing our algorithms to only ever interact with the top, we create discipline. It makes the operations so simple, so predictable, and honestly blazing fast. The restriction isn't some annoying bug. It's the whole point. It's the defining feature. All right, moving on to section 2, the why of LIFO, real-world analogies. Let's ground this with a physical model. Picture a really busy restaurant kitchen. You've got this massive pile of clean plates sitting there. When the dishwasher brings a fresh plate, where does it go? Right on top of the pile. And when a line cook needs a plate, they grab it right off the top. I mean, nobody ever tries to yank a plate out from the dead center or the bottom of the stack, right? Because that would cause a complete kitchen disaster. You only add to the top, and you only take from the top. That is perfect last in, first out logic in the real world. Now let's bring that plate analogy back to your digital life. Think about your web browser's history. When you click a link and go to a new page, the browser takes the page you were just on and pushes it onto a stack. You click another link, it pushes that new page right on top of the last one. Then, when you finally hit the back button, your browser pops that most recent page right off the top of the pile. It doesn't randomly take you back to some article you read 3 days ago. It takes you to the last one in. Last in, first out. And this brings us right back to that undo button from earlier. In a text editor, every single typing action you take is literally pushed onto a stack. When you hit undo, it triggers a pop operation, pulling that most recent action off the top so it can reverse it. Oh, and there's a third handy little operation called peek. Peeking is exactly what it sounds like. It lets the software look at the current state at the top of the stack without actually removing it. So push, pop, and peek. Those are the actual engines running your undo button. Okay, let's shift gears to section 3, under the hood, implementations. So how do developers actually build this structure in a computer's memory? There are 2 main ways. The first is an array-based stack. This uses a fixed-size array where the top is tracked by a simple little index number. Now, this is super fast, but it has a catch. Because the array's size is fixed right when it's created, it can overflow if we push too many items into it. The second way uses what's called a linked list. This one is dynamic, meaning the top is tracked by a head pointer, and instead of a fixed box, we just use pointers to chain the data together. But here's the beautiful part. Because we are strictly limited to only touching the top in both methods, the computer never has to waste time shifting other elements around. It is incredibly efficient. But, regardless of whether you're using an array or a linked list under the hood, the main takeaway here is that the top dictates absolutely everything. Every fundamental action that makes a stack revolves around managing that one single position. You push data, you update the top. You pop data, you inspect and change the top. You peek, you look at the top. Even checking if the stack is completely empty or completely full just comes down to checking the boundaries of the top. The whole data structure is literally just an exercise in fiercely guarding that single point of access. All right, section 4, the stack in action. Let's actually walk through a concrete example so you can see this in motion. Imagine an array-based stack that has a max capacity of 5 items. We'll call it S5. In step 1, our initial state is completely empty. To represent that, our top index is set to -1. It's below 0, meaning nothing is in there yet. Okay, step 2. We push the number 10. Our top bumps up to index 0, and 10 goes in. We push 20, the top becomes index 1. We push 30, the top becomes index 2. Now look at step 3, we call a pop. That removes the current top element, which is 30, and it drops the top index back down to 1. So now 20 is exposed at the top again. Finally, step 4, we push 40. The top increments back up to index 2, and 40 overwrites that space. If we call peak right now, the system just glances at index 2 and says, hey, the top is 40. So from bottom to top, our stack is holding 10, 20, and 40.
Moving right along to section 5, common stack misconceptions.
Let's do some quick myth busting because there are a few things that tend to trip people up. First myth, you can just insert items wherever you want in a stack. Absolutely not. If you allow random insertion or deletion, you totally destroyed the LIFO lot. It's not a stack anymore. It's just a normal list. Second myth, push and pop happen at the bottom. Nope, the bottom is your fixed anchor, the top is the only part that moves. If you worked from the bottom, you'd be building a queue, not a stack. And the third one, hey, my computer has a ton of RAM, so my array stack will never overflow. This is a huge misconception. Remember, an array stack has a strict fixed capacity. If your stack was built to hold 5 items and you try to push a 6th item into it, you will get an overflow error. It doesn't matter if you have 32 gigs of free memory sitting around. The overflow is about that specific local structure hitting its limit, not your whole system.
Which brings us to our final slide today, and I want to leave you with a question to chew on. What hidden, highly disciplined piles are organizing your device right this very second? Because every time your software runs a function, it pushes that data onto a call stack. Every single time code gets parsed, every time you hit undo, every time you jump between pages in your favorite app, LIFO logic is silently working right there in the background. It's such a brilliant reminder that sometimes imposing strict rules and actually limiting our options is exactly what gives us the power to solve really complex problems. Thanks so much for hanging out with me for this explainer. Keep questioning how things work, and I'll catch you in the next one.